Hello everybody, and welcome to exercise 3 on page 55. Let's take a minute to read this question together. So they'd like us to consider the basis beta, which is given by these three matrices, okay, for V, and V is the vector space of all symmetric 2 by 2 matrices. And we're going to talk about a linear transformation T from V to P1 of R. That's kind of what both parts of this question are about. Okay, now let's look at part A here. This is kind of an interesting question, a type that we haven't quite seen anything like this before. So they're giving us the matrix of T, taking us from beta coordinates to gamma coordinates here, okay, telling us what gamma is, and they'd like us to find a general formula for T of the matrix ABBC. Notice that that's a symmetric matrix. Okay, so up to this point, kind of every problem of this type that we've seen has been the other way around. It's given us the formula and asked us to find the matrix. Okay, here we're being asked to go the other way. They're giving us the matrix and asking us to figure out what the formula is. Okay, so to do this, we really have to think about what information a matrix is giving us. All right, so just kind of thinking in that direction here, a matrix is about taking us from input coordinates to output coordinates. So if we want to know what T of ABBC is, the first thing we need to know is what are the coordinates of that matrix, that input matrix, relative to the input basis beta. Okay, so we're going to start there. Take that input matrix ABBC and just ask the question, how would we build that as a linear combination of the vectors in beta, our basis beta? Okay, well that comes down to answering the question, how do we fill in these blanks? Okay, unfortunately, because there are a lot of zeros in our matrices, not too difficult to figure out what needs to go in those blanks. I'm thinking A, B, and C are going to work. Okay, so what that means then is that the vector ABC, those represent the coordinates of our input, and so what we can now say with confidence is that if we take this matrix that they gave us, 1, 2, -1, 3, 0, 1, and we multiply it by that coordinate vector, ABC, and remember again, in words, that's representing the beta coordinates of our input. What should come out over here are the coordinates of the output, T of ABBC, relative to the other basis. Okay, and we can do matrix multiplication to figure out what's over here on the right-hand side. So we'll start by taking first row times this column. That's going to give us, let's see, A plus 2B minus C. Okay, and then same thing for the other one, 3, 0, 1 times ABC, that's going to give us 3A plus 0B plus C, it looks like. Okay, and the key here, again, is the meaning of that output. These are the gamma coordinates of our output. All right, so here's what we can say then, putting it all together then. T of our input, ABBC, can be built by using these two coordinates. This times the first vector in gamma plus this times the second vector in gamma. Okay, so we're going to take A plus 2B minus C. That's going to get multiplied by our first vector in gamma. And then 3A plus C. There's our second number. That's going to get multiplied by the second vector in gamma, by x. All right. And what we just wrote down, maybe we could simplify it one thing. No reason to write just times 1. So A plus 2B minus C plus 3A plus C x. There is our formula for T of ABBC. We were able to figure it out just by interpreting what this matrix is telling us. Okay, we are ready for part B. And what I hope you notice is that B sounds really similar to A. Okay, again, suppose that the matrix taking of T from beta to gamma is this. That hasn't changed. That's the same as in part A. The only thing that's different is that now we've changed the basis in the output. Okay, in our codomain, it looks like 1 and 1 plus x. Okay, and they'd like us to, again, find a general formula for t of a, b, b, c. Okay, so the process here is going to be the same. The matrix still has the same interpretation. It's going to take us from beta coordinates for our input, and notice that our input hasn't changed and neither has beta. That's the same basis that it was given to us in the problem. So we're still going to get a, b, and c here. Those are still the input, the beta coordinates of our input. Okay, and we do that calculation. Nothing's changed on the left-hand side, so we're going to get exactly the same thing over here on the right that we did before. And the interpretation is still output gamma coordinates. Only thing that's changed is that the vectors in gamma are different now. All right, so here's what's going to happen then. So T of the matrix ABBC is going to be our first number, but this time times the first vector in gamma. So we'll get a plus 2b minus c times 1. Okay, and then second coordinate times the second vector. So 3a plus c times 1 plus x. All right, and the rest here is just some algebra. Let's simplify this. So a plus 2b minus c. Okay, if we multiply the 3a plus c through, we're going to get 3a plus c. That's going to come from taking those two times each other, and then plus 3a plus c times x. Okay, we could maybe do a little bit of grouping here. Let's see. We've got an a plus a 3a. That's going to give us a 4a. Okay, kind of nice. The c's appear to cancel out here, and then we're just going to get a plus a 2b. Okay, and that's about the best we can do, and so there would be the formula for our linear transformation. We were able to figure it out based on the matrix that they gave us.